Hello everyone. So in last lecture we discussed about layout of 2q factorial experiment when we confound AB and AC interaction effect in replicate 1 and replicate 2 partially, and after that we had discussed statistical analysis of 2q factorial experiment when interaction effect ABC is totally confounded on R replicates. So in today's lecture, we are going to discuss statistical analysis of 2q factorial experiment when all interaction effects are partially confounded. So in 2q factorial experiment, we have 4 interaction effects: AB, AC, BC and ABC. So here we consider partial confounding in 4 replicates, and we will discuss analysis of this concept. So here let us consider 2q factorial experiment with factors A, B and C respective. Okay, so here we have 8 treatment combinations: 1, A, B, AB, C, AC, BC and ABC. So these are the 8 treatment combinations, and we want to consider all interaction effects and we want to confound all interaction effects partially in this 2q factorial experiment. So since we have 4 interaction effect, so we consider 4 replicates, and in each replicate we confound one interaction effect, and this confounding is partial confounding. Our first interaction effect is AB. So first write down formula for interaction effect AB, and it is AB equals to 1 by 4 A minus 1 into B minus 1 into C plus 1. Just simplify these brackets. So we get formula 1 by 4 ABC minus BC plus AB minus B minus AC plus C minus A plus 1. Okay, so here we have positive treatment combinations and negative sign treatment combinations. So separate these positive and negative treatment combinations. So here we get one table with positive sign treatment combinations and negative sign treatment combination. So ABC, AB, C and 1, these are the positive combinations, and BC, AC, A and B, these are the combinations with negative signs. So similarly we write positive and negative group of treatment combinations for all interaction effects. So here we have interaction effect AC, and it is 1 by 4 A minus 1 into B plus 1 into C minus 1. Simplify this bracket, so we get formula 1 by 4 ABC minus BC minus AB plus B plus AC minus C minus A plus 1. So here we have positive treatment combinations ABC, AC, B and 1, and negative sign combinations are BC, AB, A and C. Similarly we write positive and negative group for interaction effect BC. So it is 1 by 4 A plus 1 into B minus 1 into C minus 1. So we get formula like this: 1 by 4 ABC plus BC minus AB minus B minus AC minus C plus A plus 1. So positive treatment combinations are ABC, BC, A and 1, and negative treatment combinations are negative treatment combinations are AB, AC, B and C. Similarly we write this for interaction effect ABC. It is 1 by 4 A minus 1 B minus 1 into C minus 1, and it is 1 by 4 ABC minus BC minus AC plus C minus AB plus B plus A minus 1. So positive combinations are ABC, A, B and C. Negative treatment combinations are 1, AB, AC and B. So for this we want to write model layout. So here we have 4 interaction effects So we use 4 replicates and we divide each replicate into 2 blocks and each of size 4. It means that in each block we have 4 experimental units. So here also randomization is at 2 stages. In stage 1, we apply positive and negative group of treatment combinations into block 1 and block 2 at random in each replicate, and in stage 2, we apply positive and negative group of treatment combinations at random in the 4 experimental units of block 1 and block 2 in each replicate. So in this way we get model layout when we consider all interaction effects are partially confounded. So here in replicate 1 we confound AB interaction effect. So in block 1 we consider a negative sign of treatment combinations. So we get ABC, AB, C and 1, and in block 2 we have positive treatment combination. So it is AC, BC, A and B. So in replication 2 we confound BC. So in block 1 we consider positive combinations. So we get ABC, 1, BC and A. And in block 2 we consider all negative sign combinations. So we get AB, AC, B and C. Similarly, in replicate 3 we confound AC interaction effect. So here also in block 1 we consider positive positive effects, and in block 2 we consider negative sign treatment combination. So we get block 1 like this: 1 ABC, AC and B, and in block 2 we get treatment combinations AB, BC, A and C. So in replicate 4, here we have replicate 4. In this fourth replicate we confound ABC interaction effect. So here in block 1 we consider positive combinations, and in block 2 we consider negative sign combinations. So we get block 1 like this: ABC, A, B and C, and in block 2 we get combinations AB, AC, BC and 1. So in this way we get a model layout when we consider all interaction effects confounded partially in 2q factorial experiment. Now we will discuss its statistical analysis, means how we get ANOVA table in partial confounding when we confound all interaction effects. So here first we will write this hypothesis. So our first hypothesis is H01 confounding is not effective versus confounding is effective. Then second is H0A, main effect A is not significant versus main effect A is significant. Main effect B is not significant versus H1B, main effect B is significant. H0AB, interaction effect AB is not significant versus H1AB, interaction effect AB is significant. The next hypothesis is H0AB, interaction effect AB is not significant versus H1AB, interaction effect AB is significant. Fifth hypothesis is H0C, main effect C is not significant versus H1C, main effect C is significant. Then H0AC, interaction effect AC is not significant versus H1AC, interaction effect AC is significant. Then H0BC, interaction effect BC is significant versus H1BC, interaction effect BC is significant. And last hypothesis is, here we have H0ABC, interaction effect ABC is not significant versus H1ABC, interaction effect ABC is significant. So when we consider partial confounding, we only delete that particular effect from that replicate. It means that we delete information of that particular interaction effect from that replicate only. So in other replicate we get we get information about that interaction effect. So in total confounding we completely delete that effect of that particular interaction effect. But in partial confounding, the replication in which we confound that effect, only we lost information about that interaction effect from that replicate. But in other replications we get information about that effect. So in this partial confounding, information about that particular effect is present, it is not deleted completely. So here we have sum of squares. So total sum of square is find out with the formula SST equals to summation I is running from 1 to 8, summation j is running from 1 to 2r. It is xij square minus correction factor, that is x dot dot square divided by total number of observations, that is 8r. Then sum of square due to block is 1 by 4. Summation j is running from 1 to 2r, x dot j square minus correction factor x dot dot square upon 8r. And this x dot j is nothing but jth block total. Then SSA, that is sum of square due to main effect A, is a square divided by 32. So here we have 4 replication, means R equals to 4, and we have 8 treatment combinations. So 8R equals to 8 into 4 is 32. So we have total number of observations 32. Then sum of square due to main effect B is SSB, and it is B square upon 32. SSC equals to C square upon 32. Now when we confound any effect on that particular replicate, then when we find a factorial effect total for that particular interaction effect, then we consider only the observations from the remaining class where that particular interaction effect is not confounded. Okay, so that's why here we lost 8 degrees of freedom, that is we lost 8 observations. Okay, so here we consider 4 replications, and in on first replication we confound AB interaction effect. So when we find factorial effect total AB, then we consider observations which are belongs to replication 2, replication 3 and replication 4. So in that case we get 8 into 3, okay, because we consider only observations from 3 replicates, so that's why we get 24 here. So SSAB is AB square upon 24. Similarly SSAC is AC square divided by 24. SSBC, that is sum of square due to interaction effect BC, is BC square upon 24. Then SSABC is factorial effect total for ABC bracket square upon 24. So here if you want to find sum of square due to error, then we use this formula to find SSE. In total confounding we directly delete effect of that interaction effect which is totally confounded. So in partial confounding we consider all sum of squares to find SSE. So SSE equals to SST minus SSB minus SSA minus SSB minus SSC minus SSAB minus SSAC minus SSBC minus SSABC. So with the help of this formula we find out SSE. Here we have sources of so here we find out ANOVA table, where ANOVA table for 2q factorial experiment in which we consider partial confounding. So in first column we have sources of variation. So here we have block effect, main effects, interaction effects, second order interaction effect, error and total. In second column we have degrees of freedom. So for block effect we have degrees of freedom 2r minus 1. So here we consider 4 blocks in which we confound a different interaction effect. So 2 into 4 is 8, 8 minus 1 is 7. So for this block effect, degrees of freedom is 7. Then for main effect and interaction effects, we have degrees of freedom 1. For error, in RBD, we know that degrees of freedom for error is t minus 1 into b minus 1. So here b is nothing but number of blocks. So here we consider number of replicates. So in 2-cube experiment, we have 8 treatment combination. So t minus 1 is 8 minus 1 equals to 7 into r minus 1. So this is the degrees of freedom for error. And for total, we have degrees of freedom 8r minus 1. So here 8 and r equals to 4. So we get 8 into 4 is 32 minus 1 is 31. So we get total degrees of freedom 31. Then in third column we have sum of squares. For block it is SSB. For main effects it is SSA, SSB and SSC. For first order interaction effect it is SSAB, SSAC and SSBC. For second order interaction effect it is SSABC. For sum of square due to error it is SSE, and for total it is SST. So with the help of this sum of squares we find out mean sum of squares. So for block effect it is MSB and it is SSB upon 2r minus 1. So here is a wrong, it is 2r minus 1, that is 7. For main effects and interaction effects of first order and second order, mean sum of square is same as sum of square for that particular main effect and interaction effect. So MSA is SSA upon 1, MSB is SSB upon 1, then MSC is SSC upon 1, MSAB is SSAB upon 1, MSAC is the mean sum of square for interaction effect AC is SSAC upon 1, MSBC is SSBC upon 1, MSABC is SSABC upon 1. For error it is MSE, mean sum of square due to error, and it is ratio of sum of square due to error upon 7 into r minus 1. So with the help of this mean sum of squares, we find out variance ratio to test above hypothesis about block effect or confounding effect, main effects and interaction effect. So for block effect we get variance ratio FB and it is MSB upon MSE, and this follows F distribution with 2r minus 1, that is 7, and error degrees of freedom. So error degrees of freedom is 7 into r minus 1, so r is 4, so 7 into 3 is 21. Okay. So for main effect A, we get variance ratio FA and it is MSA upon MSE. For main effect B, it is FB and it is ratio of MSB upon MSE. For main effect C, it is FC and it is MSC upon MSE. For interaction effects, we get variance ratio FAB is MSAB upon MSE. FAC, it is ratio of MSAC upon MSE. For BC, it is MSBC upon MSE, and for second order interaction effect ABC, it is FABC and it is MSABC upon MSE. And this variance ratio follows F distribution with degrees of freedom, with block effect degrees of freedom and error degrees of freedom. So how we give conclusion for our hypothesis? Okay, so if this FB is greater than critical value, then we reject our hypothesis that confounding is effective. Okay. So here for this case our critical value is F with block degrees of freedom, that is 7, and error degrees of freedom 21. For main effect A, if FA is greater than critical value, so here in this case critical value is F with 1 and 21 degrees of freedom with alpha % level of significance. So if this FA is greater than critical value, then we reject our hypothesis H naught A. If this FB is greater than critical value, then we reject our hypothesis H naught B, that is main effect B is significant. If this FC is greater than critical value, then we reject our hypothesis H naught C. Then for interaction effect AB, if FAB is greater than critical value, then we reject hypothesis H naught AB, that is interaction effect AB is significant. Then if this FAC is greater than critical value, then we reject our hypothesis H naught AC. If this FBC is greater than critical value, then we reject hypothesis H naught BC, that is interaction effect BC is significant. And if this FABC is greater than critical value, that is if ABC is greater than F with 1 and 21 degrees of freedom at given alpha % level of significance, then we reject our hypothesis H naught ABC, that is interaction effect ABC is significant. So this is about statistical analysis of 2Q factorial experiment when we confound all interaction effects. Thank you.